nanoparticles. This is the mechanism of plasmons. Plasmons have revealed new features of electron defacing and relaxation plasmon-phonon interactions that determine plasmon resonance quality and nature. So the metal nanoparticles are very attractive because of their size and shape-dependent properties. From the plethora of existing procedures for the synthesis of metal nanoparticles, this chapter discusses the most widely used wet chemical methods. Actually, this all material from the book of analytical chemistry. This chapter discusses the most widely used wet chemical methods which are suitable for the production of both spherical and anisomeric rod-like prismatic nanoparticles. It describes the basics of the origin of optical properties of the nanoparticles and presents some of the theoretical methods accounting for them. The optical properties of some metal nanoparticles are dominated by the collective oscillations of conduction electrons resulting from the interaction with electromagnetic radiation. These properties are mainly observed in gold, silver, copper because of their presence of free conduction electrons. Actually, the polymer-based nanocomposites have been much discussed to their technology matching properties, lightweight, ease of application, and adoption lack of corrosion, and design flexibility. However, the high dosage of nanofillers needed to meet the requirements of an effective shield marks their utility in many respects. Although biphasic polymer blends have been researched from different perspectives. They have a very different perspectives. Utilizing them as a template for microwave shielding is currently deriving enormous interest compared with the single polymer-based nanocomposites. Plasmonic materials. Plasmonic materials are metal or metal-like materials that exhibit negative real permittivity. Most common plasmonic materials are gold, silver. However, many other materials show metal-like optical properties in specific wavelength ranges. Plasmonic materials also have many good materials like copper, graphene, semiconductors. Various research groups are experimenting with different approaches to make plasmonic materials that exhibit lower losses and enable optical properties. Here is the most important plasmonic material, gold and silver. Metals as candidates for plasmonics are discussed. Metals are candidates for plasmonic applications because of their high conductivity. Actually, the gold and the silver metals have their high conductivity among metals. Silver and gold are the two most often used for the plasmonic applications due to their relatively low loss in the visible and the near edges. Copper. Metals are popularly assumed to be excellent candidates for plasmonic applications among them. Copper is the best material for plasmonics due to its lowest optical loss in the visible spectral ranges. However, would oxidize quickly and suffer severe losses due to surface roughness. Here is the electric field and the electron flow from the copper. B is the part enhanced electromagnetic field, hot change carriers, photothermal effects. You can see this from the diagram. Semiconductors and graphene. The fundamental physics of graphene, semiconductors, heterostructure as well as its optoelectronic properties are comprehensively addressed, which suggests 6 strategies of improving the performance of graphene semiconductors based upon up to electronic devices. You can see this. Graphene plasmonics. Actually, this is the structure of graphene plasmonics. You can see. Energy is transformed into the conduction band and also the valence band. Plasmonics and nanotechnology. Now, this is the next section of our topic. plasmonics, and nanotechnology. Nanoscience. The knowledge of both the spatial and temporal structure of an optical field interacting with a nanomaterial can enable a wider understanding of light matter interactions at the nanoscale. In the past years, the plasmonics community have reached a broad understanding of many light driven phenomena in the ground scale. Temporal dynamics of the excited states are instead on one side quite challenging to explore, and on the other side crucial to disclose and understand novel and unexpected fundamental scale physics and chemical processes. Unlike conventional optics, plasmonics enable unrivaled concentration of light well beyond the diffraction of light. Actually, the surface plasmons, the collectively oscillation of free electrons, as well at the interface between a conductive material, such as a noble metal, and the electric environment, support the formation of extremely confined and the enhancement electromagnetic fields at the nanoscale. Plasmonics and nanophotonics. Nanophotonics and the plasmonics is the study of light at the nanometer scale. Light can only focus to spot roughly half its wavelength in size and a few hundred nanometers for visible light. This, this limit can be surpassed by coupling light to electrons at the surface of a metal and creating surface plasma. This is the nanophotonic structure, plasmonics, spectroscopy, sensors, microfluidics, nano and microfabrication, multimodal imaging. So the next light metal interaction. The light metal interaction between a plasmonic nanoactivity and the excitant at the cup diffraction limit is a central research field in nanophotonics. Here we discussed that we demonstrated the vertical distribution of the light matter interactions at 1 nanometer spatial resolution by a coupling of MOS2 and gap mode plasmonic nanoactivities. Moreover, we observed the significant photoluminescence enhancement of vector reaching up to 28,000 times, which is attributed to the pure Sal effect and large local density of states in gap mode plasmonic nanoactivities. Meanwhile, the theoretical calculations are well reproduced and support the experimental results. So the plasmonic sensors here. Surface plasma resonance has found extensive application in chemical sensors and biosensors. Plasmas play different roles in different types of optical sensors. Surface plasma resonance transduces a signal in a colorimetric sensor through shifts in the spectral position and intensity in response to external stimuli. Basically, the plasmonic imaging, these are all nanostructures, plasmonic nanostructures, imaging techniques, etc. The plasmonic nanostructures provide new ways of manipulating the flow of light with the nanostructures and nanoparticles, exhibiting optical properties never before seen in the macro world. Plasmonic imaging is crucial for understanding the cellular behavior for biological sciences, where it's used to image and track organelles in cells, such as DNA and virus molecules. Due to the fast dynamics of the intracellular processes, it is essential to keep the cells under the native states, establishing plasmonic imaging as one of the most powerful tools for studying a biological sample. Discusses the fundamental theory of plasmonics, enabling deeper understanding of plasmonic technology, details number of methods for modern design and optimization of plasmonic nanostructures, induces step-by-step design guidelines for active and passive plasmonic devices. So it is shown that natural modes are not only excited but actually dominate the intensity and shape of the observed plasmonic image. Plasmonic and nanoelectronics. Nanoelectronics refers to the use of nanotechnology. These are all the nanotechnology department. In electronic components, the term covers a diverse set of devices and materials with the common characteristics that they are so small that interatomic interactions and the quantum mechanical properties need to be studied extensively. Plasmonic nanostructures. Plasmonic nanostructures provide new ways of manipulating the flow of light with nanostructures and nanoparticles exhibiting optical properties never before seen in the macro world. Plasmonic photodetectors. Plasmonic photodetectors are attracting the attention of the photonics community. Plasmonics is the attractive because metallic structures have the ability to confine light by the coupling at a magnetic wave to charge carriers oscillation at the surface of the metal. Here is the plasmonic photodetector cycle. Single particle structures and the coupled structures, then the metal insulation shell structure, graphene plasmons, and the doped semiconductors. Actually, these are the plasmonic metal structures, and these are the plasmonic non-metal structures. The next one is the transistors. Plasmons also relate with the transistors. This is the field of plasmons. This plasmon field effect transistor collects the plasmonically induced hot electrons from the physically isolated metal nanostructures. These hot electrons contribute to the amplification of the drain current. Plasmonic field effect transistors. This is the ratio frequency of maximum transistors. You can see here. Plasmonic memory devices. Nanoscale resistive random access memory electronic device integrated with a plasmonic waveguide providing the functionality of optical readout. The device fabrication is based on silicon insulator compatible approach of local oxidation of silicon, which enables the realization of and low optical loss channel photonic waveguide at the same fabrication step. This plasmonic device operates at telecom wavelength of 1.55 micrometer and can be used to optically read the logic state of a memory by measuring two distinct levels of optical transmission. We attribute the changes in the optical transmission to the creation of a nanoscale absorbing and scattering metallic filament in the silicon layer, where the plasmonic mode resides. You can see from this diagram, this is the plasmonic memory devices view. So the plasmonic biomedicine. Actually, the use of plasmonic nanoparticles for biomedical applications has been extensively researched.